Hey folks, so obviously AI is advancing very, very quickly. We've had Gemini, CLI come out in the last few weeks. Claude Code has been absolutely smashing it. Grok 4, the development version or whatever, is coming out soon. GPT-5, blah, blah, blah. So if you're at all in the AI space, you know that things are moving very, very quickly. Now, if you followed any of my stuff before, you know that I'm really interested in simulation, Python, AI, that whole kind of overlap. How do we build digital twins? How do we make decisions using digital twins and simulation and that sort of thing? Now, I've discovered something really interesting. Let me show you. This is using AI to actually run and analyze your simulations. So if you go on the SimPy website, you'll come across this machine shop example. So this is a sort of pretty common an example that people use. It basically runs a machine that makes parts and it kind of breaks down now and again. So I took that code. Let me just show you exactly what I've done here. I've taken that code, whacked it in a file here. I've extracted the parameters and put them in a separate config file. So now if you imagine the simulation as like a black box, and then you've got your input, which is this file, which is the config that goes into that black box. And then I've also got the output from this simulation being saved as a CSV file. Now, the output is relatively unopinionated. I'm just saving I can actually show you what the output looks like. I'm just saving the time, the name of the machine, the event type, whether it was a repair, breakdown, or the parts being produced, and then the total number of parts made on the right here by that particular machine. Now, I actually did all that with Gemini, so I can just show you my commands quickly. So the first one was move the parameters from machineshop.py into their own config file. Great, it did that nice and easily. Now separate the output data from the machine shop code. I want you to record the raw data from the simulation and save it in a CSV file. And then, oops. And finally, now write instructions in the Claude, because we're going to use Claude Code, not Gemini for this, in the claude.md file for how to configure the simulation, run the simulation, and where the output data goes. And then we get this. So this Claude MD file is our context for the AI. It tells it basically how to configure the simulation, what the parameters do, how to run the simulation. So it says when you're ready, go and run this command, Python machineshop.py, and then helping it kind of understand where the output goes, what the raw data log looks like. Now, if I fire up Claude, and I'm using Claude here, not Gemini, because I've tested this with Claude. I haven't tested this with Gemini. I think Gemini is actually a bit better at writing SimPy simulations, by the way, but Claude is very well engineered for this kind of agentic kind of testing and running and doing stuff on its own. So let's just go straight into it. I have not done this before with this particular example. So let's say we want to analyze and I'm going to delete this. Let's delete this CSV file. So this thing hasn't got a CSV file to work with. Okay, delete anyway. Okay, so I'm actually going to add an important point here in the Claude code. Do not edit the shop simulation code directly. Let's see if Claude can run a few scenarios and give us the throughput for those different scenarios. So come up with 5 scenarios and run I'm not even going to say what simulation it is because I've given it the context here. Come up with 5 scenarios and run the simulation, analyzing results and presenting the throughput for each scenario. Okay, let's see how Claude gets on with that. So it's brewing. So I'll create 5 different scenarios for the machine shop simulation, run them and analyze the throughput results. So this is the AI actually working now with the simulation that we've already got. It's going to play with the config. It should, I expect, run the simulation independently itself. and it'll present the results to us. So here we go. It's first of all creating a script to run the 5 different scenarios, and then it's got these 5 scenarios come up with these baseline configuration, high reliability machines, fast processing with frequent breakdowns, more machines with slow processing, quick repairs with moderate reliability. And then it's going to do a final step where it analyzes these results and calculates the throughput. Okay, so it's got a run scenarios.py file. Cool, so it's got these scenarios in a dictionary here. Okay, that's pretty cool. Right, okay, interesting. So it's actually creating this config like so. Right, okay, cool. Let's let it modify that. Or let's let it create that. So it's not touching any of the actual simulation code itself. It's just kind of treating that as a black box, as we've instructed it to. I have seen this work very well with where you have the input code, the input parameters defined in a YAML file, and then you load in that YAML file, ideally using Pydantic. I found Pydantic pretty good for that. And then you can validate your data on the fly. Okay, brilliant. So here we go. Oh wow, it's run the results already. So okay, scenario 3, fast processing, frequent breakdowns. Okay, so it appears to have actually run all of these through this run scenarios.py file, which must import the machine shop and run it. But yeah, okay. Can you visualize the results? So it's identified scenario 3 as having 2 times faster processing with 24% higher throughput despite twice as many breakdowns. That sounds good. Now, of course, in reality, what you would do is you would go and verify these results yourself in a situation like this where we actually haven't really got like the tight kind of data validation steps, but in a more robust simulation we can trust these runs a little bit better. Okay, cool. So it has got a visualize.py file, so we're going to just accept that at face value. Okay, cool. Nice. So here's our throughput comparison across scenarios. Top left, we've got our throughput in terms of parts per week. That is the scenario, that'll be scenario 3, the one that sort of was a standout scenario. Let's see if I can make this a little bit smaller so we can read it. What happens if I just make that full screen? Oh, there we go. Then an efficiency analysis is quite interesting. So efficiency metrics, parts per machine. Okay, and it seems to have made a mistake on parts per minute. So that would warrant a little bit of closer attention. But yeah, parts per machine there, that's quite interesting. And look, we've got a bit of a different trend between scenarios 3 and 4 and what we see in the pure throughput. Now this spider diagram, that's pretty cool. So you've got your processing time up at the top here, which scenario 3 does pretty well in, but it underperforms in the mean time to failure here. We know that it has more frequent breakdowns. They've all got the same number of machines and the repair time is the same. And then it's got some key insights down here. So bam, this is pretty cool. This is like 80% there. I'd want to go through and check the working, but right away I've got a decision-making document. And how long have we been working on this? About 5 minutes, unless I've completely lost track of time. This is really interesting. So there you go. That's how you can take a SimPy simulation. You can work with AI, for example, Claude Code or Gemini CLI. You can get it to actually run your simulation, analyze the results, and give you some output on the fly.